we're going to talk a bit more about the way that maths is applied in industry, specifically in the design and construction of networks. So for a long time, mathematics has been fairly inaccessible. Often if mathematics is used, it's tightly held and not widely shared. But what we've seen recently, however, is a number of industries finally starting to leverage the power of mathematics and then bring it into the hands of consumers and smaller businesses. So there are two key factors that are contributing to this shift. Applying mathematics frequently requires significant computational resources. The increased adoption of cloud infrastructure, led by Amazon Web Services, but closely followed by Google Cloud and Microsoft Azure, is reducing the barrier to using mathematics in the day-to-day operations of many companies. So we can now connect to powerful mathematical solvers from any device connected to the network, which is another case of fiber optic networks. In addition to the advances we've seen with infrastructure, we've seen advances in the field of human-computer interaction and user experience design. So what this means is we've gotten better at figuring out how to connect a user with a task that uses math. A key insight into the human-computer interaction is the way that humans are kept in the loop as critical decision makers. There's a balancing act between handing over decisions to the machine and letting the human make a decision. So the advances in infrastructure and human-computer interaction combine to position mathematics as a tool that can be used by anyone without the need for specialist training or equipment. So before we delve into our own work of bringing the power of maths to bear, I'll go over some more familiar examples. So Uber, it's mathematically connecting drivers to passengers based on ratings. It's charging the fare type based on supply and demand, and it's optimizing the routes for drivers to reach a destination. Users don't need big brains or big machines to benefit from maths in this form. So Swissport is another example of a business application for crew scheduling. They're the largest global provider of airport ground handling services, and so have a really complex list of variables when it comes to creating a crew roster. So they have to consider things like skills, hours worked, union and labour rules, and all of this needs to be re-optimized in real time based on unpredictable time horizons like plane delays, people calling in sick, etc. Another application is train planning and mine scheduling. These benefit from deploying maths on cloud infrastructure and then connecting users to it through a simple user interface that presents them with familiar ideas and patterns. So I've just evangelized the application of mathematics to industry. What I'll do now is actually give an example of a problem that is being solved behind the scenes. So the example is a traveling salesman problem. The problem is simply, if I have this set of cities, what's the optimal route to visit each one so that my salesperson is spending the least amount of time traveling? The problem is a classic in operations research, and it's a good example of the fundamental principles that we apply. So the first principle is to have rules or constraints. So in this case, the first rule is visit every city, and the second rule is use the road network to travel. We then have costs, and in this case, the cost is just the distance between each pair of cities. The objective of the problem then is to minimize the cost within the constraints that we have. So the solution to this problem as a purely mathematical problem has been solved dozens of times using a bunch of different methods. No one tries to solve this problem at scale by hand anymore. The challenge today is how to best allow real-world users to solve this problem by giving them enough control to set the constraints and costs.
Okay, so now let's look a little bit deeper at what Pat's just been talking about. There's no doubt that deriving or establishing economic value for a fibre network deployment can be sliced and diced in a myriad of ways. And we know that one of the largest costs is the build of this network. And in particular, the construction of any new path, whether that be aerial or underground. There are many factors that induce complexity in the decision-making process. So it's really important that we really think about the implications of where our engineering time is spent, where all the various parties in the end-to-end workflow of establishing this network spend their time and critically think about what needs to happen next in order to realize the economic value initially perceived or dreamt of at the early stages. So when thinking about these cost implications, we can think about it in a number of layers. And specifically for us, we really hone in and focus most of our energy on the physical layer or layer one of the network. Yes, there are other organizations and opportunities to use optimization and automation at the other layers. However, we've deliberately attempted to really hone in and become expert at the physical layer. We feel that problem is large enough on its own, So what we're going to talk about today in terms of the examples, the case studies, is really in relation to the physical layer, the physical network, and the assets as pertaining to the outside plant. So when you look at the diagram on the left, we see the key inputs. So again, when Pat was talking about how optimization works or the way that we use it, it's all in terms of inputs and constraints. So when we think about these networks geospatially, we have the demand data, which may be single dwelling units, multi-dwelling units, it could be businesses, it could be other commercial type buildings, it could be hospitals, schools, government buildings. There could be that there is the poles and the aerial span layers. So whether there is existing conduit that needs to be maximized, or whether we're talking about absolute new build where we'll be running down new sides of streets yet to be constructed. There is also the roads and street network. This can be used for offsetting and things like that. So there's a constraint that can be built off following road lines and things like that. And of course, there's the hubs and other key points where these networks come together, such as the central office. Now, on the right-hand side are a number of constraints. These are a number of examples. There are many of these, but for example, there's split ratios that limit the amount of splices we can have or splits in each hub of the network or each tier of the network. There are closure sizes. So we may feel that in certain areas you may not be able to go over a certain size of enclosure or vault. There's the fiber cable capacity itself. And there are natural limitations here, particularly even when you're trying to lash fiber, if you're going for an aerial build versus those on other tiers of the network and you're going underground. And of course, there's the fiber cable length, because we want to ensure that this network will work, which means there is a natural physics-based limitation on what can be done and how far we can go from the central office to the actual demand point that we're trying to serve. So ultimately, the benefit of applying optimization here is we really want to try to create a fully connected network. The way to do this is to prescribe an architecture which ensures all the constraints are well documented, and that way when the machine is doing the hard work, it is working in accordance with those limitations and applying those to the inputs that are provided. Okay, so here's a traditional approach, and for many years, and even when I really started as an engineer quite some time ago, the way that I was introduced to design and the way that I was trained was I was given a number of documents, and in that case it was, at least they were electronic, but they could be printed. My objective was to scan those documents and then try to understand what the rules were, what the requirements were, and there was obviously a number of guidelines versus definitive rules that I needed to adhere to when it came to the design process. On top of that, I was sat next to a very experienced engineer who at the time knew almost every facet of the local exchange, or exchanges rather. It was a downtown area, so there was 5 exchanges or central offices in that area that he knew intimately. He also knew a lot of the vault locations and how much capacity were in these. So when I was doing my initial designs, if I couldn't find what I needed in the records, the database of record that was typically out of date, I could always ask him and he knew. So that was the way that, I know that a lot of us have been brought up in the way of thinking. So when we look at it here on the left-hand side, we see there are these constraints, these inputs. We have the in-field feedback from the field. This could be via address validation. It could be via constructability write-out. So there's also construction constraints. For instance, what type of boring patterns are permissible? Where can we or can we not set up a boring machine? Do we have to trench? Can we get access to actually have a cherry picker to be able to lash the fiber in certain areas? Are there railways? Things like that. There's the actual geospatial data, and then, as I said, there's the architectural constraints or the physical or the physics-based constraints of the when it comes to the optics. As we move to the right, there's designers that try to interpret these guidelines and requirements. Now, I know that speaking to a lot of the larger organizations here and around the world, a lot of the VPs that run these organizations have a very similar problem. They all say, if I've got 200 designers, I get 200 different designs. And what becomes more of a problem is there is a natural angle of divergence as you move to the right. As those designs, now somewhat unique, are being written out or checked for constructability and then eventually built, there is always going to be a divergence away from that initial design. And this happens more prevalently when there's more and more designers that have more subjectivity induced into these designs. So the process is somewhat broken. Yes, it's sort of worked for many, many years, but with the power of the math, the optimization that Pat mentioned before, we should be really doing a better job in trying to understand and adopt these sort of approaches to make this far more bulletproof and scalable. I think we all agree that having those sages is a rare thing these days, and it's not possible to have these people giving the same information across the entire team, because ultimately we're all people. We don't always say the same message the same way every single interaction that we have. So what we really are trying to focus on here is a different approach that we've worked very hard, and others have as well, over the last 3 or 4 years in particular, and trying to bring the math to bear. So in the center now we have these key core elements, or schemas, architectural documents, and requirements. And right in the middle we have the machine, or the optimization and automation that will make use of these constraints and input data. Now what we have is if we think about the deployment of a network, initially we have a leadership team that may have the vision of a network that needs to be deployed or upgraded. Beyond that, we have the planners that start doing the high-level planning. They could be doing feasibility plans, trying to understand what the costs are going to be. And then we have the designers that will eventually be then breaking this plan down, and working on the actual designs of the network. From there, we have the field validation teams. And this could be with respect to initial address validation or demand point validation. We're seeing more and more now people are using technology such as LiDAR and high definition imagery, and then using image processing to capture the appropriate data out of those images, to replace people physically driving around and taking information. The other key input here could be understanding exactly what the pole loading is. So looking at pole data, strand data, things like that. Constructability write-out is self-explanatory, taking that design that the designers have completed and checking to ensure it actually can be constructed. From there, we have the construction vendors, and typically there are multiple of these out there, or at least multiple teams. Now, when we think about the interoperability problem here, we want to ensure that everyone's looking at the same source of truth, and they're working off the same set of requirements. In this model, where we put all these key components into the center, now what happens is the relationships and data flow happens through the core or the hub of this diagram. So no longer are these planners and leaders having a data flow directly between one another without going through the core. This way they are compliant with this interoperable schema. And this schema or schemas is consistent through the entire workflow. What we've seen over the last year and a half at least is those that adopt this in the most broad fashion seem to yield the greatest results. So this, a few years ago, this was very much seen as something very strange, and we were looked at as if we had two heads for the most part. These days, with these case studies we're seeing with us and other organizations that are adopting similar models, the economic value is right in front of your eyes. So it's very exciting to take on this approach, as scary as it may be. So the core here is all the interactions are via the standard and interoperable schemas and approaches that are driven by the core and the hub. And that's how people communicate. And it becomes relatively seamless because obviously we use automation and optimization to do so. So let's look at some of the complexity of deployments. Here's just one example. Let's assume there's 90,000 homes to pass or demand points. Now let's look over an example of, let's say 0.8 assets are required per home pass. So now we're looking at 72,000 assets to think about. Translating this into tasks, if we don't really break down into subtasks at all. So let's assume one task per asset. Now in the office, when we think about the different roles that different people hold within the office to make this a reality, we can say safely that there's going to be at least 6 tasks per transaction or per asset from that initial home pass. So now we're looking at 432,000 tasks to manage and coordinate. In the field, let's say there's 4 tasks per asset. And again, we're not going to go down into the subtask level, but even then the numbers are looking pretty scary between these last 2 numbers on the right. Now, historically, we hire large teams to maintain, manage, sequence the work to ensure that those tasks, now between the office and the field, we're looking at over 600,000 easy to ensure they're working in the right order. And it's obviously, let's face it, we're humans. We're not going to always get it right. The sequencing is going to be out. There's going to be delays. And this puts these projects in jeopardy. So when we think about the complexity, it's really important to think about the scale here. Now, humans struggle with that type of scale generally. That's why we typically need more and more people, and we try to muscle the problem. Taking on an optimized and automated approach, you don't need as many people trying to do this because the grunt is being done by the machine.
All right, well, thanks, Paul. I think this is probably a good time just to go through a quick little demonstration of how software is actually used in network design. So while I'm going through this, just a few things to kind of keep in mind. So I'm going to be using some data to drive the demo. So something to consider is, do you have any data readily available in your business to begin designing? I'm going to be implementing some constraints. So you could think about what sort of constraints you have in your own organization as it pertains to network design. Then you can think a little bit about, could you actually work this approach or this technology into your approach? And then think about what does it mean for any current projects you might have? Where could you sort of see it accelerating things a bit? So for the demo, I'm just going to jump back into my web browser and just use our web version of Fond hosted just online. I'll go in and create a new project. So every new project we create is just a new design. All right, so first thing I'll do is just give the project a quick name and then choose the architecture. So I'm going to do this design in a fairly small area, and I'm just going to choose an architecture that is usually pretty good in an area like this. So centralized 1:32 split with going out to an 8-port closure. So in each sort of tier 2 cabinet, we'll have 2 1:32 splitters going out through a variety of cable sizes to these 8-port closures, often called a terminal or an MST. So I'll save that architecture now. So as Paul mentioned, one thing we need to have is input data. So I can go in and find some address data that we've got in our database that we maintain for address data. And I'm just going to go down to Mansfield, Illinois. That's where I've been doing a few designs lately. All right. So I'll pull in some input data. So it's just going to be the addresses and the streets that we'll be using to create our network. So this sort of approach is great for a high-level design. It's not going to, you can see that the input data isn't going to be going across one side of the road or down both sides. We're just going to use street center lines, but this gives you a good initial idea of some of the potential metrics you'll see in your network. So I'll import that data now, and then the one other thing I'll do is just place my central office location. And this could be a central office or a tie-in point. So what I'm doing here is I've created all the physical constraints. So in the traveling salesman problem earlier, I talked about we need to serve every one of the cities. In this case here, we've got to serve every one of these address points, and we need to do it using these orange lines. We're not going to use all of those lines, but every one of those lines is a candidate location for a cable. So I'll go ahead now and hit generate design. So while that's happening, I'm actually going to do another design as well, just in parallel, and I'm going to compare the two designs to each other. So we'll go demo 2. So in the other case, I used centralized split with an 8-port closure. I'm now going to use centralized port split with a 4-port closure and just use 1x132 splitter in that cabinet there. And I'll pull the same data in as before. So draw the polygon again. So I'm reasonably sure this will have exactly the same input data as before. Yeah, 356 addresses. I'll import that into the project. So you can, of course, upload your own data. So if you had poll and span data from an electricity co-op, for example, you can go in and upload those. But just in this case here, it's really simple for us just to use our own database of addresses and street networks. So now I'll hit generate design, and I'll actually explain the problem that it's solving. So it's taking every one of these address points and all of the street locations, and it's creating a candidate network. So that's a network that contains all the different possibilities that the network might look like. And once it's finished analyzing that problem, it goes about finding all of the closure locations. So that's those often called a terminal that are going to serve the drops. And then once it's found all of the terminal locations, it'll connect each of those back up to the cabinet, which houses the splitters. And then each of those will then be connected back up to the central office. So while that's running, I'll go back over to this one and just see the design that we kicked off earlier. So this is the design with the 8-port architecture. And so we can see that if I turn off some layers here, we've got each of these addresses connected back up to these closures, and we can have a maximum of 8 addresses per closure. And so you can see it's done its best to connect as many addresses as possible to reduce the number of terminals. So every terminal in this design has a cost, as does every cable length, and so that's what it's tried to minimize. And while minimizing that, it's created the network. So you can see each of these closures gets connected back up to these cabinets with the splitters in them, and each of those cabinets gets connected back up to the central office. So the other design's finished now as well. So just to make for comparison's sake, let's have a look at that. You can see here we've only got 4 addresses per closure now. And again, they go back to the splitter cabinets. So in these cabinets, they're slightly different. They've only got a single 1x32 splitter in it. So we've got 2 different architectural approaches here. So what we expect to see is some different quantities. So I'm just going to compare some cable lengths in this comparison. So each design produces a bill of materials, which can be sort of as detailed as we need it to be. So looking at the architecture with the 8-port closures, we can see we've got a little bit of 48 fiber cable, quite a low 24 count, and about half the amount of 12 count. In the design with the 4-port closure, we see a very different distribution, and that's because in this case here we're using smaller terminal sizes, so typically that leads to longer drop cables. So the distribution of cables between the drop tier and your access tier is changing. As you can see, we're using a different number of splitters, so six splitter cabinets as opposed to 13 here, because in this case here we've only got a single 1x32 splitter in each cabinet, so that's expected. And we've also got different numbers of buried terminals. So 49 in the 8-port case, and then 101 in the 4-port case. So I'm happy to share these designs with anyone who'd like to, in the comments or questions, just say that you'd like me to share the designs with you. I can send them through for you to have a look at. But for now, I think we'll just go back to the presentation. So just to go over what we did, we created a design for 2 small networks, and we compared 2 different architecture configurations, And we looked at some key design metrics between each of those configurations. I just looked at the costs that are typically main drivers in the network, but there will be smaller variations in other materials as well. And those areas are about 536 homes, and we did all of that in maybe 5 to 10 minutes. So back to Paul.
Thanks, Pat. So, just to one of the things that really stood out for me, and coming from that traditional approach, traditional thinking. I'm an engineer by trade, versus the way that the way that Pat thinks and the way that these problems can now be solved. And looking at that demo as it was running, really you can see the power of this approach. Really as engineers and leaders in this industry, we can spend far more time collaborating on the results of these sort of outputs and the results of this design approach, versus spending a lot of time coming up with the initial design so then we can have the conversation. So there's a very important distinction here, and really a really important shift in how we slice and dice our time and where we should focus our energy and think deep on the problems that are in front of us. So in terms of a case study, the one we're going to go through now, we're talking about a network that we started talking with a customer a little bit over a year ago, and from when we started to when the first lit customer was on, it was less than 12 months. And in this case, the initial footprint was 27,500 homes. The initial CapEx investment was $63 million. And initially it was projected that the construction would take 5 to 6 years, purely because of there was some concerns that due to the rural nature of this project, it was going to be challenging to find the appropriate level of resources to conduct the design, or rather the construct the design in the run rates that were traditional in those sort of areas, if that makes sense. So the organizations that were looking at the feasibility were saying, look, looking at standard run rates of construction out here, this is going to take us 5 to 6 years. Now, looking at where we're at now, looks like it's going to come in within 3. So one of the key distinctions here was that this is towards this evolving design approach. Everyone involved worked very hard to understand and collaborate on exactly how we were going to make this possible. Everything from the co-op that's involved, the design and engineering partners, the equipment supplier, the construction management side, and ultimately the construction vendors. So even when it came to the selection of vendors, they were advised that this was going to be performed digitally or paperless, depending on how you want to look at it. So thinking again back to that diagram where we had the hub of the one source of truth, and thinking about that interoperability side of things, what this yielded is the following. So from a planning perspective, 200 miles less of distribution fiber, cost saving of 4.6 million as far as we've seen so far, and that's the funding that's been used to date. High level design, there was implementation of a very fast agile feedback loop, which meant that any feedback could be incorporated into future designs for sub areas of the total footprint. And the collaboration was a huge cost saving at that, from that perspective. There were minimal amount of stakeholders required in order to yield that sort of result so early on in the workflow. Initial walkout. So we talked a little bit about this before, but the fidelity of the data was improved dramatically by using a digital approach. It's a lot easier to, if you are, always linking back to that single source of truth, to ensure that any shifts, changes, updates of information such as poll information, make ready, things like that, go back to that one hub for everyone else to use. So it really minimizes complexity in handoffs and delay in handoffs. So in terms of low-level design, the fidelity of the data from the field teams, as I said, came back very quickly. It was almost instantaneous. The the tasks that were completed were synchronized in real time. And this also allowed for greater automation in terms of the artifacts required, such as splice tables. In terms of construction management, 4 people are managing this, the construction of this network, which we feel is a very good result. So far, there have been 0 delays. The way that the workflow has been sequenced, and again, that's been done, that's an automated approach, has ensured that crews aren't being sent out for work that cannot be completed. You know, people are released, the construction crews are released to do work that is actually able to be done. So there's been no teams delayed or stood down. There's been no lost days in terms of work because something's missing. And again, there's this access of information across the end-to-end. So everything from the issuing of materials, keeping very tight track of inventory, the actual construction itself, invoicing and overall reconciliation with as-builts is all happening very, very smoothly. In terms of the construction, so far we're seeing less than 2% of fibre reel wastage, which is an amazing result. In terms of infield variations, it's next to none. In terms of the construction so far, there's been already $700,000 of savings. And as already mentioned, huge reduction in the perceived overhead or forecast overhead to run the construction of this project. So from an ongoing operations and maintenance, the service provider already has visibility into what the real built network is due to the way that the as-builts are being captured. And this already can be assessed, analysed, and they can identify, okay, from the savings we've found, what does the increase in footprint really look like? Initial projections say 30% increase, but I know that they're looking at to see who else they can serve, which is a better result for everyone. So as I said, one of the key objectives here was to, there's an opportunity here to serve to provide broader reach in these rural communities, which obviously desperately need connectivity.
Right, so Paul's just sort of been talking a bit about the end-to-end approach. And so what I'm going to talk a bit about now is how we have, throughout that whole process, we have a design that is evolving. It's an evolving OSP design. So this comes back to thinking about the way we're using maths to design the network. We use maths, the same maths throughout the whole approach. All that changes at each stage is the information that we have. And the earlier that you begin using those maths, you start to get some information, and you can use that information for all sorts of things. So I make the analogy between this evolving fibre design and a 7-day weather forecast. So when you're trying to plan your weekend, 7 days out, the forecasters don't have all the information, but they've got some information, and that information is useful. You'll know whether you should plan to head to the beach or stay at home. And then as we get closer to the weekend, the forecasters get better information, and so the predictions improve. So the way that sort of translates to fibre design is we take a similar approach. We use the same maths throughout to design the network, but as we get closer to construction, instead of the weekend, our information improves. So we might find out, after doing our initial network plan, we might find out where some gas lines are and move the cables to one side of the road. We might find a bit more information about who owns the poles, or find out that there's a new development going up, and so add in some new address data. Once you've got that high-level design, you might then walk it out and and do some permitting as well. So that's then more information that then feeds into that design. And finally, you've got your construction pack, and that's going to be used to send out to segment the work. The whole way through, we've got a design that gives us information, and that information allows us to do things like apply for funding, order equipment and materials, hire crews, and finally, change direction if needed. You can find out far earlier on whether something's going to work or you're going to have more trouble in that high-level design stage, because we've got a real design to sort of have a look at, and our estimates are more close to reality. So throughout the evolution of the design, as I mentioned, we create new information as output, and the new information is used as inputs for other processes. So some outputs are used to inform different decisions, or to ask new questions like, should we maybe change architecture here? It doesn't look like this is going to work. Other outputs are used for ordering the materials, and then finally the design itself is incorporated into other systems, so that digital design is incorporated into a digital system where network operations management and maintenance can take place using that design. So back to Paul.
Okay, so in terms of some examples, and this is really just to summarize some of the concepts we've been talking about that really underpin this evolving design or this dynamic design approach. So on the left-hand side, we have a cost-optimized fiber-to-the-home network. So in this example, the intent is to maximize the use of existing conduit, minimizing new build, and perhaps it's using the smallest possible cable for each tier of the network, whilst leaving, let's say, and as an example, you want to leave 15% spare in a number of tiers of the hubs within the network. So they're the sort of constraints that can be applied for a standard or a fiber to the home or similar type of deployment. In terms of the diagram in the middle, where we have a fixed wireless network with an FTTH endpoint. So here the objective was we want to be able to eventually serve or be able to serve every single home or demand point within this area, the service area, with fiber to the home. So we wanted fiber all the way, but because of the way we wanted to use our funds available, or the way we wanted to gain funds, we needed to phase this project out. So initially, where possible, we want to serve up to 10 homes via an LTE antenna, but obviously we want to ensure that there's the capacity in the network for that final fiber to the home where need be. And that gives you lots of options as a service provider, as a consultant, or as an engineer to help the decision-making process. Do you really need all that funding now, or can you start making a return on your investment from the fact that you've already got customers lit, even though the last hop is LTE, is wireless? So it gives you many, many options. And in this case in particular, we ran the scenarios that to generate the costs and what the cost or cash flow forecast looked like when it came to the difference between 2 or 3 different types of phases in the project. So it became very, very powerful for the end cooperative. And all the way on the right here, we have a fiber cellular front backhaul network with small cells. So in this case, maximizing use of existing assets while minimizing additional build, ensuring all cells are connected. So in some of these examples we've seen, we already know that the locations of the smart light poles are fixed. So it was a matter of, okay, out of all these opportunities, which ones should we use? And therefore, what is the resultant fiber or the cheapest, shortest path fiber to serve all these light posts? So in terms of the approach, at the end of the day, this is still relatively new. We feel that there is significant importance in trying to undertake this type of approach to designing and constructing networks, to using this evolving design approach. What's interesting is on Saturday I was at a sports game for one of my sons, and I was sitting next to a veteran who I'd never met before, and initially he said, "Hey, who are you supporting, red or white?" And I responded red, because I wasn't quite sure if I was sitting in the right place and whether he would be upset if I was in the wrong side of the field. And we started talking, and he obviously remarked about my accent. And he said, "And what do you do?" And I said, "Oh, look, I'm in the telecommunications industry." And he looked at me and he had this big smile and he said, "Boy, have you guys made the world small." And that was a really interesting comment, coming, I felt, from a 70-something-year-old gentleman. And he made me really think hard about that. And it's like, yes, there's been so many advancements in networks, and we are far more connected as not only organizations but also as communities, and ultimately the world is a lot flatter because of the way we can communicate. But the reality is there is still a huge problem in unserved and underserved communities, and really there are still so many problems and challenges we are facing and trying to solve as an ecosystem and as leaders in this industry. And I'd like to think that those of you on the call and others in your leadership teams and your broader, ecosystem that you play can work harder and think more critically about the real problems that we need to solve out there to make this go a lot faster, smoother, to produce the economic values for our communities that we serve. The only way to do that is to shift where we spend our time thinking, away from these transactional small things like drawing these networks by hand. I mean, really, we shouldn't be spending time doing that anymore. We should really spend all our time collaborating, thinking deeply about what do these results tell us, how do we as a team, as an ecosystem, get these networks built quicker to serve these communities, to help unleash and uncover the talent out there from people that we haven't even tapped yet because they're not connected into this ecosystem. So we feel this is a really good initial step, but we can't do it ourselves. The problem is too big. We need everyone, we need all your help to make that a reality.
All right, well, that's the end of the presentation, but we definitely have some time for questions. So I'm just going to sort of check here and see if we've got any questions come through. I'm not sure if Nick's got access to the list of questions.
Hey, yeah. So quite a few of questions have come through actually, which is good. So we were asked a question around I guess when you were talking about the level or the access network pool. But the question is, are we working around other sort of optimization modeling for the layer, I guess the layer 2 and 3 of the network, or how does optimization fit into those different levels?
That's a great question. So what we've found, the technology that sits in 2, 3, and 4 in particular, a lot of these routers, switches out there, they dynamically optimize the networks in a lot of cases. We are not experts in those layers. We typically work and partner with organizations and network engineers that focus on those layers. And we find that approach allows us to complement each other's skills to ensure that on our end, what we're building is going to serve their needs from their perspective and the layers in which they play in. So in some of these case studies we discussed, we were in those initial conversations with not only the equipment providers, but also the engineers that were really thinking about the MPLS of these networks and things like that. So when it came to that, we were then looking at, okay, what does this induce in terms of the physical layer, and specifically from our perspective, okay, what does the OSP layer now need to look at or look like in order to be able for your MPLS to function the way you want it to function? So there's between the network engineers working in those specifically in those layers, and also the dynamic optimization that occurs, which is akin to the dynamic optimization that occurs between 3G and 4G cellular sites. They do, the optimization is done on the fly dynamically. So, I think it's important that everyone focuses on where they need to focus and where they, what they know and what they're good at. So it should all be part of the mix. It should all be part of this collaborative approach, and then it's a matter of working together to ensure that each layer is going to function the way it's intended.
Awesome, thanks, Paul. Pat, I think this is a good one for you. There's been a few questions around how we source and how we work with geospatial data and data in general, and sort of where we have some of that data available. Is it just the States, or is it Canada as well? So I guess the big question is, where does the data come from that we are just using?
Yes. Oh, sorry.
And sort of where else is it available?
Yeah, cool. So, I mean, at the moment, what we're doing is trialing whether the way we're delivering this data is working. So we've worked with a commercial parcel data provider in the US, and we're looking to partner with others as well, just to figure out the best way to actually connect users with that data. and it seems like it's valuable to customers. And so now we're looking ahead to taking a similar approach to different markets. So the United Kingdom actually has really great input data that we could use in a similar way. So we could absolutely pull that in, and in the same way that I drew the polygon in Illinois, that would work in the UK. Canada, there are a number of commercial data providers. It's a bit more challenging there because they seem to be broken up mostly by province rather than having a national database. But then there are some other providers out there. This is what we're considering, who provide building footprints that have been scraped digitally. So Microsoft, I don't know if you saw in the New York Times recently, they had a picture of America. It was amazing, and it's all automatically generated. So that it's, the last few years we've been kind of waiting for someone to finally perfect the ability to pull in rooftop data and digitize that, and I think we're finally actually seeing it get to the point where it could be useful, which is really exciting because that means that they can use that same mathematical approach anywhere in the world to get data for anywhere. So I think what we might see in the next 6 months is a lot more, is us hosting a lot more data in different markets. Our target market is the US. We're focusing on that at the moment, but the next to come after that will be Canada and the UK as well. And we're seeing a lot more activity in Africa as well. South Africa has great parcel data.
Just to add to that too, Pat, one of the things that we've found is a lot of organisations initially, when thinking about this approach and how to use this approach, are concerned by the quality or the fidelity and the sheer amount of data they have or they don't have. So many of our initial discussions are really around the data sets, and because when we talk about optimization, we mentioned constraints and input data. We do spend a lot of time talking about that and showing ways that automation can be applied to actually curate and to clean the data without always necessarily going out to physically inspect. So it's for those areas or those cooperatives, or whether it be a municipality or whether it's a large tier 1 telco, when there's data sets that aren't quite right, there's ways that can be attacked, and there's many organizations that are tackling that problem, but we see that quite often. So we know in the past we've had people say, oh, I'm not sure if you can help me, my data's pretty trash. Well, I think it's important that you don't let that stop you trying to take that forward.
You've only got to clean it once, and then it's good, and you can keep using it for a number of applications. It's a pain sometimes to do that initial cleaning, but yeah, once you've done it, you can iterate on it a number of times, and it only gets better.
Awesome. Another question is around someone's saying that they've sort of done the network feasibility and they're looking to get started around sort of that design phase and engineering phase of the network. What's the sort of, or how do they get started using sort of a maths-based approach?
Yeah, look, that's a great question. We actually get that quite a bit, particularly from cities or municipalities, smaller ones where they've already done their own feasibility. There was an example of one, recently here in Colorado, where we were approached by a city. They said, "Hey, look, we've done our feasibilities. Can you help with the design side? And where does that go from there?" So the short answer is absolutely, you can get started by really coming together and working through, having a look at what you've got so far. What does the feasibility tell you? What are the plans? What's the vision for the network? What's the objective of having this network? That way, us and others in the ecosystem can ensure that it's going to be fit for purpose. And then when it comes to looking at the design, engineering, construction, there's ways to model, compare, and analyze different architectures. So I know that some people get really concerned that they haven't made that choice yet. It's okay. As you saw, Pat ran in the demo, he ran 2 different architectures. Yes, they were small areas, but they ran in minutes. So the power of the math is out there to run larger areas, even if it takes 10, 15 minutes for an area of 10, 30,000 homes, you can have comparisons to talk to think through and decide upon within hours to days. So it's all a matter of understanding that you have some sort of inputs, having accessibility to those inputs and having accessibility to the people that are thinking about the architectures to start modeling, showing results, and then iterating from there. And as Pat said earlier, one of the most powerful benefits of this approach is the ability to iterate very, very rapidly. So that way you've got all these different results of comparisons to make those decisions quickly. So it's never too late to start.
Awesome, thanks, Paul. And I think maybe we'll do one more just before we finish this off. But I think it's a pretty good question, and it sort of links on pretty well with that last one. So what are the best practices for owners, construction firms, engineers, and in a similar diagram to before, and working throughout the project in the iterative way that we've described? And what role do contract terms play versus sort of that informal relationship between the people involved?
I'm not sure if I understand the question, but
I guess a big one is around that cultural fit versus a contract strictly saying this is exactly what we're doing, and how does that all come together to help, or what are the best practices for working in the iterative and maths-based approach way?
Okay, so let me try to answer that question. So as we've said, one of the big, most powerful elements here is that a lot of the complexity in the construction of the network is handled by the automated approach. So, for example, with some of the case studies we're seeing now that are where the construction is, in inverted commas, paperless or digital, the way that the work is sequenced, it is released to the field, the way it is completed is driven in such a way that it does a few things. One is it simplifies the ability for those involved, whether that be the construction crews, the superintendent company, the general contractor, and the end service, the people that are actually buying the design or the end deployment, for them to communicate, because now they can, the actual data from the construction is what it is. It is objectively caught within the applications, the processes and systems deployed in the field. So when it comes to, I'll give you an example. In one of the current projects we're working on, there's 3 construction crews, and they race between each other. I think there's 3 or 4, but anyway, they've gamified this approach where they look at how many tasks each team has completed per day, and they've got their own internal reward system for themselves. Now, because they're using the applications on iPads and tablets, they're forced to behave a certain way in the field, and they're capturing really good, accurate information. What that also means is when it comes to paying for that, as soon as they complete those tasks, the other organizations that need to know exactly the footage, the quantities that have been used. So everyone from the logistics team that are looking at inventory and tracking that, they know exactly what's been used, all the way through to billing. There's no arguments as to what was done because it was caught in the field when it happened, which means these guys are all getting paid on time. So everyone's very happy, right? So when it comes to the real, the subject project, everyone can get on and think about the things that they need to think about, and they don't have this noise of what is happening out there, because that is transparent. It is crystal clear what is and isn't happening. So it drives a very different type of conversation. It actually elevates the conversation to the things that really matter. Does that help?
Yeah, I think that answers it.
Yeah.
Awesome. Well, I think we'll leave it at that. Thanks everyone for joining us today. We hope you got a lot out of the presentation. And webinars can only do it so much justice. So if you've got time or any more questions, please reach out. We'd love to talk further and potentially go into a bit more detail around your specific rollouts and data that you have. One more thing is that at the end of this, you'll be given a quick survey. If you've got any questions around how the content and even what you'd like to see next from us, that'd be awesome to hear. But yeah, I think that's it for now. Thanks for joining us.
Yeah, if there's any unanswered questions, Paul and I will do our best to try to respond to those in the next couple of days. So,
Awesome.
Thanks everyone.
Thank you.
Thanks everyone.